Okay, we're going to go through the full derivation of the Bessel function of the first kind. This all begins with the Bessel equation, which is, of course, x squared y double prime plus xy prime plus quantity x squared minus p squared times y equals 0, where p squared is some number. It tends to vary by specific problem type, and that's what sort of differentiates one Bessel equation from another. We've done the typical utilizing the Frobenius method. This guy has p's and q's that are not defined at 0, and so we have to use this. When I take this and its derivatives and substitute it into here, this is what the relationship turns into. You can go ahead and check that on your own if you like. You can see the first series begins at n equals 0. The next series begins at n equals 2. So this first series is going to generate the first two terms without the second series. Let's look at those first two terms. When n equals 0, we get r squared minus p squared times a naught equals 0. We would prefer for a naught not to be 0. That means r squared equals p squared, or r equals plus or minus p. This is the Indicial Equation, which means these are the solutions for r that we'll use for the remainder of the problem. When n equals 1, also the first term is the only one that produces any portion of the series. And now it's r plus 1 squared minus p squared, a1 equals 0. In this case, we're in a kind of a bind. Whether I want a1 to be 0 or not, the value for r is already chosen. It's equal to p. And if you look, p plus 1 squared or 1 minus p quantity squared, no matter what I substitute in for r, these aren't limited to being 0. These will have specific solutions for p that make it 0, but we want p to be a general value that can really take on any value. That means if this can't be 0, a1 has to be 0. And if a1's 0, this recursive relationship skips orders, which means all odds are 0. So now we can focus on just the even powers and generate what the relationship is between these future terms. That's going to give us the solution. So when n is greater than or equal to 2, so for all the future terms, this is what we end up with. We end up with n times the quantity 2p plus n times an plus an minus 2 equals 0. All I've done here is I worked out what that guy is and I factored out. So that simplified produces this. Again, you can check that yourself if you like. And this gives me the recursive relationship. So for all the remaining n's, an is given by negative an minus 2 divided by n times 2p plus n. Now, we actually want r to be equal to p, and that's the substitution we've made in order to simplify this into this. You might wonder where the r went, and that's because we've chosen the first solution. So from here on down, our choice is that r is equal to p. Now we can start generating terms and see what the relationship is. Remember, we start at n equals 2, so a2 is going to be equal to negative a naught divided by, with n being equal to 2, this is 2 times 2p plus 2, or 4 times p plus 1. A3 we can skip because all the odds are equal to 0, so our next term is a4, and a4 is going to be negative a2 divided by 4, and then it's going to be 2p plus 4. So I can think of factoring a 2 out of here and leaving behind a p plus 2, so it's really 4 times 2. And then I'll go ahead and substitute in what a2 is equal to. That's going to make positive a naught divided by 4 squared. There's the extra 2 to factor out, and then it leaves p plus 2 and p plus 1. I'm already starting to see the pattern, but let's do one more term and prove it. A6 is going to be equal to negative a4 divided by, this will be 6 times 2p plus 6. Again, I can think about factoring out the 2 from this. That'll leave p plus 3. Factoring out of 2 is going to be 2 times 6, which is 12, and I'm going to rewrite that as 4 times 3. So that way there'll be another 4, so when I substitute this in, it's going to be a naught, be negative this time. And then it'll be 4 cubed for the third 4 that was part of the 12. The other thing that was part of that was a 3, so it's times 3 times 2, and then inside it was p plus 3 times p plus 2 times p plus 1. Okay, I'm ready to write out the general relationship then. It looks to me like a to the 2k, I'm going to replace n by k so I can double it, is always going to be negative 1 to the k times a naught, and then the denominator is going to be 4 raised to the power of k times k factorial, and then times a weird thing. This won't be a factorial because it always begins at p plus k, and it goes all the way down to p plus 1. So that's what I got to write, is that it's p plus k times p plus k minus 1 all the way down to p plus 1. If it were a factorial, it would finish with 1, but we don't know that p is 0, and so we can't write it as a factorial. So that's it. That's as simplified as this guy gets. Now, I can make one more condition, and that's going to allow us to find this simplified. And that is, my final condition is that, let's suppose that p, as the solution to this guy right now, is limited to being an integer. Which means p could be 0, 1, 2, 3, but it's got to be an integer. And we won't look at negative p yet. We're just going to consider positive p first, because we know this guy represents positive p. The second thing I'm going to do is I'm going to assume a value for a naught. I'm going to assume a naught is equal to 1 over 2 to the z times z factorial. And again, z now is the integer value that p takes on. So if on our original equation, if this guy were a perfect square, then we could go ahead and use this, okay? Okay, so let's see what the ramifications are of using this substitution for a naught. You might wonder why I've chosen it. Remember, a naught's just an arbitrary constant that comes with the series. The whole purpose for choosing this is it dramatically simplifies this. And let me show you how that works. So, a to the 2k is now going to be equal to, well, the 2 to the z, I can call 4 to the, or 2 to the 2k, because all 4 is 2 squared. So now it's 2 to the 2k plus z. So that's the first item in the denominator. The numerator just has negative 1 to the k in it, because a naught's gone, it's replaced. And the first term is 2 to the 2k plus z. The next term is just k factorial, and that stays the same. This is where the real magic is going to happen. Remember, what I've done by placing z factorial in the denominator of a naught is I've in essence tacked a z factorial onto here. Keep in mind that p actually is z. It's an integer, which means all of these are z's. So this is z plus k minus 1, all the way down to z plus 1. And now z factorial takes us all the way down to 1. That turns this just into z plus k factorial. It wasn't a factorial before because it didn't stop at 1, but now it is. This has made that happen. So now I can just say the denominator is z plus k factorial. And you can see now that our a2k term is a lot easier to represent than it was before, okay? Now let's fill in what the original series said was the solution, because now that I have my general a, I can replace that. So y, which is really y1, the first solution, is equal to negative 1 to the k. Whoops, got to write the summation. Summation k equals 1 to infinity of negative 1 to the k. Now, when we consider x, remember, we only ended up with even powers, so we can't use odd x's. We're only going to use even. So it's x to the 2k. But then that's plus r, so that's plus z, because r was p, and p now is an integer, so plus z. And then the denominator is all of this stuff. It's 2 to the 2k plus z, k factorial, and z plus k factorial. Well, when you have this summation, it not only is the first solution to this equation when p is an integer, but it also has a special name. This is called the Bessel function, and it's a Bessel function of the first kind, so we use the subscript z on it to indicate that this is only when p is an integer. If p is a non-integer, then it's not going to look like this, because that was essential to making this factorial substitution, was that z was an integer, so the regular rules for factorials hold. So it's jz of x, and that's this. That is the Bessel function of the first kind. Now, what we're going to do in our next class period is we're going to talk pretty extensively about some of the properties of this function. This function is going to turn out to be really important to us in Chapter 6 in solving PDEs. And this probably is arguably one of the most important equations in applied mathematics, just because of how much the Bessel function comes into play. All right? Okay, in the next video, we're going to talk a little bit about the gamma function. In particular, we're going to look at the Bessel function of the second variety and where the gamma function comes into play. All right?